The bomber should already be dead. It's late afternoon over occupied Europe, and the sky looks like rusted metal. Flak bursts hang in the air, black flowers blooming at 12,000 feet. A four-engine bomber staggers through them, skin torn, engines coughing. Inside, the crew is way past fear and well into exhaustion. The pilot's yoke is shaking in his hands. One engine is feathered, another is smoking. The formation has long since disappeared into the haze ahead. And now, as if this isn't enough, there's a new problem. A streak of gray flashes past the left window. Then another. Fighters. The intercom explodes. Fighters, 10 o'clock high. Lead, we've got bandits all over. Tracer rounds slash past the nose. The pilot hauls the bomber into a turn, every muscle in his arms screaming. He knows what the manual says. Do not exceed bank angle X at speed Y. Do not enter steep turns at low altitude. Never flirt with a stall in combat. He looks at his airspeed. Too slow. The controls go heavy, then light, then heavy again as the airplane edges toward the one thing a bomber is never supposed to do in a fight: stall. You can almost feel it with him. The sudden mushiness in the yoke. The subtle, sickening shudder as airflow starts to break away from the wings. The warning whispers of a machine about to quit flying. On paper, in every engineering office back home, this bomber is out of options. If he tightens the turn, physics will take over. One wing will stop flying before the other. The aircraft will snap, roll, tumble, maybe even shed a wing. A heavy bomber is not built to dance. But up here, paper doesn't matter much. Hang on, the pilot mutters into his mask. Maybe to his co-pilot, maybe to himself, maybe to nobody. He does something he was never taught in any classroom. He eases the power back, not forward. The nose wants to drop, but the wings, miraculously, keep biting into the air. The bomber slides into what feels like slow motion, almost flying on the edge of nothing. And then he feels it, a strange, heavy pull. The props seem to grab more air, not less, even though he's at a speed that should make them useless. The airplane, this big brute of aluminum and rivets, starts to bend around the turn in a way he's never felt before. The fighter flashes across his nose, overshooting the turn, the German pilot no doubt already squeezing the trigger on empty air. Down in the belly, the waist gunner swears he can feel the airplane shudder and pivot like a man trying to dodge a punch. He fires on the now exposed fighter, tracers curving away. Somewhere in that chaos, somewhere between the stall buffet and the grinding howl of engines, a bomber does something it was never designed to do. It dances. What those men don't know, what the official training manuals don't say, is that back at their base, a mechanic with a crescent wrench has quietly broken the rules that define how this airplane is supposed to fly. And according to some of the people who were there, that tiny act of defiance meant 1,000 crews like this one lived to see another sunrise. So here's the question. How does a nobody in a grease-stained coverall change the way a $100 million war machine behaves? And why did the factory engineers insist that if he tried, the airframe would tear itself apart? This is the story of the illegal propeller twist, of James Jimmy Nagel, the garage mechanic who made bombers dance, and of the thin, dangerous line between the rules that keep machines safe and the risks you take when lives matter more than paperwork. Before we meet Jimmy, we need to understand just how unforgiving the world of WWII heavy bombers really was. If you'd been a young man in 1943, climbing into a bomber for your first mission, there's a chance someone would have quietly told you not to bother learning everybody's name. Not because they were cruel, because statistically you weren't all coming back. In some bomber groups, the life expectancy of a crew wasn't measured in years, or even in missions. It was measured in weeks, 10 sorties, maybe 15 if you were lucky. The airplanes themselves were marvels of engineering for their time. Massive multi-engine machines that could haul tons of bombs hundreds of miles. They were designed for stability, for predictable handling, for surviving battle damage. But they were not designed to outturn fighters. Not really. Take any of the classic heavies. Long wings, high aspect ratios, huge fuel loads, fantastic at cruising in a straight line, good at carrying bombs, terrible at pulling tight, quick corners, especially at low speed. And low speed is where combat gets interesting. When a formation breaks, when a bomber loses an engine, when a pilot has to dive, weave, or jink to shake a fighter, that clean world of design assumptions vanishes. Suddenly you're at high angles of bank, marginal airspeeds, messy airflow. Stalls are right there waiting. Every bomber pilot knew fear of the stall. A stall isn't the engine quitting or the aircraft falling out of the sky, as people casually say. It's more subtle. It's when the wing, pushed just a bit too hard at too steep an angle into the air, can no longer keep the flow attached to its surface. Lift collapses. One wing goes first. The aircraft lurches, twists, sometimes drops a wing with terrifying speed. In a fighter in clean air, a good pilot with training can feel that edge, play along it, even use it tactically. In a heavy bomber full of fuel and explosives, in turbulence and flak, you do not play with stalls. Every training booklet drilled that in. But paper rules are written for ideal conditions. Combat is a long way from ideal, which is exactly where Jimmy Nagel lived. Nobody at the time would have picked Jimmy out of a crowd. No general stars. No stack of engineering degrees from MIT. He came to the war from a small garage, the kind of place where you fix farm trucks on Monday, a schoolteacher's car on Tuesday, maybe tune a local kid's hot rod on Friday night. He wasn't a test pilot. He wasn't a designer. He wasn't supposed to question what the smart men with slide rules back at the plant had decided. He was there to change oil, to swap out dead engines, to make sure the bombers left the ground in the shape the manual said they should be in. Officially. Unofficially, he was a problem, because Jimmy had grown up in the kind of world where factory settings were just a suggestion. You know the type. Maybe you've met someone like him. The guy who can listen to an idling motor and tell you the mixture's wrong by half a turn. The one who can drive a pickup on mud it has no business crossing because he knows the feel. In the garage, he'd seen specifications and charts, sure. But he'd also seen engines that survived just fine outside those specs and others that failed within them. By the time he put on a uniform, he'd already learned a dangerous habit, trusting his own hands more than the book. On base, Jimmy watched bombers take off, and he watched them come back when they did. He learned the sounds of damaged airframes limping home, the clatter of loose panels, the cough of engines hit by flak, and more than anything, he heard the stories the crews told. Came around too hard, she started to stall, had to roll out and give him my tail. Couldn't tighten the turn, he just sat back there and chewed us up. Over coffee in chilly mess halls or leaning against landing gear in the dark, the same theme kept coming back. These big machines were wonderful straight and level. But when fate pushed them off that line, when they had to get slow and ugly, they turned into victims. What Jimmy also knew, and what most of the air crews never thought much about, was that there was a key component connecting the raw muscle of the engines to the delicate bite of the air. The propellers. To most people, a propeller is just a spinning fan. To Jimmy, it was something else entirely, a set of twisting wings. If you could stop one in mid-air and grab a blade, you'd see it's not flat. It's shaped and angled along its length. At the root near the hub, it's more twisted. Near the tip, it's less so. Why? Because a propeller blade is cutting a spiral path through the air. The parts closer to the hub move slower than the tip. They need more angle to bite the air at the right amount. The tip racing along needs less. Get that angle wrong, too steep for the speed, and the blade stalls just like a wing. Get it too shallow and you don't get enough thrust. Now add another complication. Most WWII bombers used variable pitch propellers. They weren't just fixed pieces of metal. They could rotate around their long axis, changing the angle at which they met the air. Fine, pitch for takeoff and climb, more like a low gear. Coarse, pitch for cruise, more like a high gear. Where exactly those limits were set, how quickly the blades could move, how much they could twist, what the default was at low speed. That was the realm of the factory engineers and test pilots. and they were conservative for good reasons. Set the props too aggressive at low speed and you could overstress the engines, over-rev them, vibrate the airframe, maybe even put the blades into conditions where flutter, catastrophic bending and shaking could tear things apart. On their charts, they'd drawn a thick red line. Do not cross, the airframe will explode. Maybe not literally like a movie explosion, but in the deadly way that matters, metal failing, blades shedding, engines coming off mounts. Back at the plant, nobody was going to sign off on a configuration that gave a tiny combat edge at the cost of a possible structural failure. They had careers and consciences and companies to protect. But Jimmy wasn't sitting in an office looking at charts. He was standing on the hard stand, wiping oil off his hands, staring at a bomber with 20mm holes stitched along the fuselage and bloodstains on the floor. He saw that red line very differently. Did that line protect the airplane, or did it protect the paperwork? The more he watched, the more a question gnawed at him. Why were they willing to trade away low speed, high-angle performance, the exact zone where their friends were dying, for safety margins that might never be used? Imagine you're Jimmy, standing there in the wind with the engines ticking as they cool. You listen to another shaken pilot talk about getting chewed up in a slow turn. You look at the huge Hamilton standard props or Curtiss electrics or whatever the model is in your imagination, and you think, those things are barely working at combat stall speeds. We're not asking them to pull. We're idling them along because that's what the book says. What if we're leaving thrust on the table? What if the real dance, the one that could save lives, happens just outside that safe red line? Jimmy starts small. On the ground with the engines off and the props still, he climbs a ladder. In his hand is not some exotic tool of aerospace science, but the same thing he's been using since the garage days, a worn crescent wrench. He's not bending metal blades with brute force. That's a myth born from bar stories. Those blades are thick, strong alloy. You don't just grab and twist. What he does have access to are the linkages, the mechanical guts that tell the propeller governor how far to rotate those blades and when. Most variable pitch systems of the era have stops, screws, collars, physical limits that say, this far and no farther. They were set at the factory to keep everything within the engineer's comfort zone. Jimmy loosens one, just a hair. He marks the original position carefully. If this goes wrong, he needs to be able to put everything back exactly as it was. He's not suicidal. He turns it maybe a quarter turn, maybe less. Just enough that when the props go to low speed, high power settings, the blades will bite a little more. The engines will grunt a bit harder. The thrust curve at the ragged edge will shift. He tightens it back down. On paper, nothing has changed. In reality, he has just nudged a factory-perfect machine out of its certified envelope. And if anyone up the chain of command finds out, he's going to be in very real trouble. Who does he tell? Not the colonel, not the visiting engineer from the manufacturer who drops by to inspect the base, clipboard in hand. He starts where any good mechanic does, with a pilot he trusts. Look, he says, maybe over a cigarette stub, maybe in the shadow of a wing. I've adjusted something, a little, on your bird. You're gonna feel it when you're slow and dirty. Don't panic. Just see how she handles at the edge. The pilot stares at him. Out there, he's the one betting his life on this little adjustment. Is it legal? He finally asks. Jimmy shrugs. It's war. We don't know the exact words exchanged. Accounts differ. Like so many wartime stories, this one survives in fragments, post-war interviews, half-remembered anecdotes, the kind of tales told at reunions and misremembered in memoirs. Historians will argue about details. Did Jimmy Nagel really exist under that exact name? Were there several mechanics doing similar things? How many crews did they actually save? But the core idea that frontline mechanics sometimes rebiased propeller systems for more low-speed thrust, no matter what the factory said, isn't fantasy. Somebody somewhere took that risk. So imagine that first test. Empty airplane, no bombs, minimal fuel, clear day. The pilot takes the bomber up alone, or maybe with a trusted co-pilot and a flight engineer who knows enough not to put anything in the logbook they don't want the brass reading. They climb up to a safe altitude, level out. The pilot runs through the usual checks, controls, mixture, RPM. So far, she feels the same. Then with a long, steadying breath, he starts the dance. He slows the bomber down, one knot at a time, keeps the nose up, feels the weight building in the controls like wet sand. The stall horn, if there is one, flickers. He banks gently, then harder. Feels for that familiar shudder, the warning that the wing is about to give up. But this time at the edge, something's different. With power eased back, what any textbook would call a power-off stall setup, most bombers would go mushy, then tip. But with Jimmy's tweak, as the nose starts to sag, the rebiased props don't just spin uselessly. Their blades, now angled for more bite at low speed, dig into the slow air like claws. Torque and thrust and asymmetry swirl together in a way no factory chart predicted. The pilot feels a heavy, almost unnatural pull through the turn. Not the clean, easy pull of a graceful fighter, but a kind of brutish heave, like a wrestler throwing his weight into a pivot. The bomber doesn't snap over the way he's been warned it will. It shudders, yes, it complains, but it keeps flying. He rolls out, tries it the other way, sneaks the bank angle up a few degrees past the old never-exceed line. Again, the edge is different. The cliff is not where it's supposed to be. He brings it home, adrenaline still shaking in his hands. On the ground, Jimmy is waiting with a look that's half curious, half afraid. Well, the pilot thinks about all the lectures he's heard, all the diagrams of airflow, all the confident voices from the test centers far away. Then he thinks about that strange, ugly, wonderful feeling, a machine of 20 tons twisting just a bit harder than any fighter pilot behind him thought it could. She shouldn't be able to do that, he says slowly. But she can. This is where the story gets complicated. In the clean, comforting version, word spreads, tests are run, the factory blesses the modification, and Jimmy Nagel gets a medal. In the messier version, the version that sounds more like war, word spreads between crews quietly. Between trusted mechanics, between men who have seen too many friends not come back. Students of aerodynamics and professional engineers will rightly point out that what Jimmy is doing is dangerous. That shifting propeller geometry to favor low-speed thrust can introduce new stresses, new vibration modes, new ways for things to go catastrophically wrong. They're not wrong, but here's the awful calculus of total war. From Jimmy's perspective, the catastrophic thing is already happening, every week. In the skies above, he's not choosing between safe airplane and risky airplane. He's choosing between documented safe and maybe slightly more likely to rip itself apart under extreme conditions versus definitely more likely to stall, definitely more likely to die when the fighter tightens his turn. So the whispered proposition goes around. If your number is going to come up anyway, do you want every legal safety margin the factory ever imagined? Or an illegal edge at the very moment the Grim Reaper climbs onto your wing? Imagine being a pilot hearing that pitch. What would you choose? Some say no, they trust the book, or they've seen what happens when experimental tweaks go wrong. Others, the ones who have already had fighters sit comfortably tucked behind their tailplanes one too many times, say yes. With each willing aircraft, each small adjustment, the base becomes a kind of unofficial test lab. Crews start playing with the power-off stall technique in training sorties. Not the wild, full-brake, spin-inducing stall you're warned about. A controlled flirtation with the edge, pull it around, throttle back just before the wing gives up. Keep a touch of rudder, let the nose drop just enough. Then feel for that rebiased thrust to haul you around. None of this is in the manual, but the war doesn't always care about the manual. Out in combat, odd things start showing up in after-action reports. If anyone bothers to write them down accurately. Enemy fighter overshot during hard turn, rear gunner scored hits. Evasive maneuver at low speed unexpectedly effective. The aircraft responded differently than in training, tighter turning radius observed. Can these outcomes be cleanly traced back to Jimmy's wrench? No, war is too messy for that. There are too many variables: pilot skill, weather, enemy mistakes, dumb luck. But when you talk to the old men decades later, when their hands shake and their voices drift, some of them will say something like, "There was this one mechanic, I don't know exactly what he did to our props, but after that she could turn, just enough to make the other guy miss." Historians, doing their due diligence, try to count. How many aircraft were modified? How many missions did they fly? How many engagements played out differently because a bomber could outturn ghosts? The ghosts being both the fighters on their tail and the statistical fate hanging over them. You'll hear numbers: 100 crews, 500, 1,000. You won't see those numbers in official procurement documents. You'll see them in interviews, in memoirs, in the margins of history where emotion lives. So was it really 1,000 crews saved? We may never know for sure. What we do know is this: it doesn't take many lives changed for a small, local trick to echo across a war. One bomber that dodges a fighter makes it home. 10 men live. Those 10 men in future missions drop bombs more accurately, survive more sorties, mentor younger crews. The survival of one crew ripples forward. Now multiply that by every base where some variant of Jimmy's work was going on. Different names, different wrenches, same instinct. Push the machine where it was never meant to go because the enemy isn't playing by the manual either. Somewhere along the line, inevitably, the grown-ups notice. An aircraft comes into a depot for heavy maintenance. A factory engineer examines the propeller governors and frowns. A stop screw is not where the blueprint says it should be. What idiot touched this? An inquiry is launched. Questions are asked. Jimmy, or someone like him, finds himself in a small office under fluorescent lights, hands folded, listening to words like unauthorized modification and liability and court-martial. The engineer, to be fair, isn't a cartoon villain. In his mind, he's trying to keep people alive, too. If a prop blade fails, it can slice into fuselage, fuel lines, crew. His red line on the chart represents not bureaucracy, but worst-case scenarios he spent years trying to prevent. Jimmy doesn't have the math to argue. He has stories. Sir, with respect, the book isn't flying those missions. How do you put that kind of conflict on a graph? In some tellings, the commanding officer quietly buries the issue. Maybe he's flown enough himself to understand. Maybe he pulls the engineer aside and says, "You want to keep our loss rates where they are, be my guest. But don't you dare take away anything that's keeping my boys alive." In others, Jimmy is ordered to put everything back the way it was. Some bases roll back the changes. Others, further from the eyes of the inspectors, keep them in the shadows. Reality was probably a patchwork. That messy, uneven adoption is part of why this story never made it into glossy post-war histories. It doesn't have the clean lines of a famous fighter design or a new radar set. It's not a line item in a budget. It's not a named program. It lives instead in that half-light zone where the official version of the war ends and the improvisations of desperate men begin. So why does it matter now? Because wrapped up in the tale of the illegal propeller twist is a question that doesn't go away when the war ends. When should the rules give way to the reality in front of you? We like to believe the people who write the rules know best. That if something is forbidden on a chart, it must be for a good reason. And most of the time, that's true. You would not want your airline pilot today deciding, on a whim, to tweak the propeller controls because he thinks it might give him a slightly better climb rate. Modern aviation is built on the bones of accidents and experiments and painful lessons. The safety margins exist because someone, somewhere, learned the hard way what happens when you cross them. But in war, especially in a world like the 1940s when information and testing were limited, the margin for improvisation was wider. And the pressure to bend the rules was immense. For Jimmy, Nagel, and men like him, the rule book was not a sacred object. It was a starting point. He wasn't a genius designer. He didn't overturn aerodynamics. He nudged. He biased. He shifted the performance envelope slightly toward the realm his crews actually fought in. Low speed, high stress, bad air. He accepted new risks to mitigate old ones. Did he know in detail what could go wrong? Probably not. Did he understand more than most gave him credit for because his hands had been deep in engines since he was a kid? Almost certainly. At the end of each day, he went back to his bunk not knowing if his bet had paid off. That's the part the stories rarely dwell on. We get the heroic version, the bomber that dodged death. We don't get the nights a mechanic stared at the dark shape of an airplane on the field and asked himself, did I do the right thing, or did I just get lucky today? If you had been in his position, watching the casualty lists climb, listening to pilots describe their aircraft as sitting ducks when things got slow, what would you have done? Would you have kept tightening the bolts exactly where the engineers told you to? Or would you have picked up the wrench? And if you'd been that engineer back at the factory, seeing a mechanic tampering with the careful balance you believed was keeping thousands of airframes in one piece, how forgiving would you have been? Stories like this one don't give easy answers. They're uncomfortable because they show us that sometimes both sides of an argument are right. The engineer is right. You can't let every mechanic improvise on safety-critical systems in peacetime. Jimmy is right. In the heat of combat, with death already screaming through the sky, not taking a bet on a small, calculated edge can feel like a worse sin than breaking the rules. Somewhere between those truths is the space where war is actually fought. In the decades since aviation has moved on, fly-by-wire jets, digital fuel controls, there's not much room anymore for a lone mechanic with a crescent wrench to alter the fundamental behavior of a frontline aircraft. And yet the spirit of what Jimmy did, the willingness to look at a finished system and say, for this specific brutal reality, we need something different, that still matters. You see it in software engineers bypassing standard procedures to patch a city's power grid during a disaster. In medics improvising equipment in the field when the supply chain fails. In test, pilots quietly exploring the edge of the envelope so the syllabus can be rewritten for the next generation. All of them in their own way are asking the same question Jimmy tacitly asked when he cracked those propeller stops loose. When do we trust the rule book? And when do we trust the person in direct contact with reality? The story of James, Jimmy. Nagel may never get its own chapter in the thick academic histories of World War II. You might not see his name on a plaque in a museum. But the next time you see footage of a lumbering bomber twisting through flak, or a grainy photo of a smiling crew climbing down from a shot-up airplane that somehow made it home, you might spare a thought for the hands that tuned that machine. For the quiet men in greasy coveralls who saw the war not in broad strategic arrows on a map, but in a bolt turned half a degree tighter, a screw loosened half a turn, a propeller biased just a little farther toward the dangerous, life-saving edge. The men who knew that sometimes, in the worst conditions imaginable, knowing when the rules matter less than the lives, is what makes the difference between another entry on the missing list and 10 young men walking, dazed and grateful, back across the tarmac as the sun comes up. If you've stayed with this story all the way to the end, ask yourself, how many other illegal tweaks and half-forgotten improvisations sit buried under the official version of history? And in your own life, when the safe, printed rule collides with what you know intimately about the real world in front of you, whose judgment will you trust?